Oh. That was embarrassing. Well, my first confidence on his thing since like November. So, I mean, you still want to eat them.
I'll take anything on the on this. Really, the boys not.
Don't eat before. Okay, sir, if you want me to be here at 3:45, I get out of school at 3:20, but I don't get to come down here until 3:30. I have 15 minutes to get in my match with the car, to ride somewhere, get food, come back, by 3.
I don't know. The boys not talking about. I can't. Boys not food. Yeah. Maybe I don't know. Well, last time I went to chance, last like an hour and a half drive. Yeah. So we were like base or something. Although it's taking this time, that was a long night. Yeah. I feel bad for the varsity.
They probably don't eat them.
Hey, man. Yeah, I think you look for varsity. Get used to that. I wish it was. I wish it was. I mean, very the varsity. Only after varsity.
I do too.
And our games are on Tuesdays and nights, and we're not in school the next day. Yeah, mine's not like this.
So, finger dust yourselves. It just broke, fell apart. Mr. Kaufman hit the wrong button at the wrong time. That's why there's two of them. So I ended up having to restart the live stream. I don't think everybody ever got back into it again.
I just watched it like after.
Which I figured that, I mean, that's one of the advantages of doing it this way is while I don't have them pre-recorded, all I have to do is readjust the live stream if it breaks and it will record class like normally. You can skip through to wherever you want to skip through. Warm-up problems here for us today. Got warm-up problems here for us today. Allie Grace. I like it. That's Miss Mazako's favorite pick too.
Yeah, just go back. Yeah. Oh, yeah. There's always them.
There. There.
I'm not even gonna get to go to the tournament next weekend. Why? No, scholarship day, it's okay. I'm gonna take the afternoon, and I'll be there for half of the afternoon. Well, what about, it's a 2-day tournament. Ours isn't next weekend. I think ours is the JBA tournament next weekend. Ours is a 1-day tournament.
Okay, if you don't say hi.
We have one.
No, it's okay, it's okay. I don't want you to get forced.
20th and the 21st.
It's okay, it's okay. Don't want to be forced.
I don't think ours is at Rock Hill now. Dang, I wanted to play Anna's team. Huh? Is Anna? I don't know. I don't know their schedule, 'cause sometimes, so I put them in some different ones than us. I'm interested to see how they'll do this weekend. Huh?
That was pretty much good.
Alright, Claire going next week. I really don't know, because I have been trying to figure out a way for me to be at scholarship day and the tournament, and there's like no way, because I have to be at Lisa McCray at 8 in the morning, and then,
Make a clone.
Huh?
Make a clone.
I
And then
can't do that.
send your clone to one, and you go to the other.
Every couple months.
I can't do that,
Why?
because I'm not that smart.
It's also illegal.
It is?
Yeah, you're not allowed to clone people.
Wait, you can actually clone people? The
I mean, they
clone
never
way-
actually cloned a person, but they have cloned like animals.
But then scholarship day, we have an essay, we get 2 hours for an essay from 8 to 10, go for 2 hours for that. And then we have interviews
Your home
with,
count gang, and I got one more problems on the board for you guys today.
we have interviews with department heads, there's 3 interviews, they'll each do like 20 minutes.
You didn't want to go there anymore?
No, but come on, because I got
We do.
like almost half tuition off from there from scholarships, they gave me like merit scholarships.
Yeah, so why would you even do it?
I lost my Alzheimer's.
If I get more scholarship money, it'll be less than where I want to go.
Yeah, but you're.
I've never worn it. I lost it immediately.
I don't know. I don't know. I don't know.
Should we make a nice photo?
It's literally only been there for 2 years, and it's just a mingled up a mess of all their other animals.
What?
Their pre-vet program at Lake Bay is only like a bunch of classes that mixed in from other majors.
Why?
Because it's like only 2 years old.
Read off 4 home. Read off 4 home. Let's see what we got. Where's Wes? Where's Wes?
What is synthetic division? Is that like with the house?
The house?
No, that's long division.
Oh.
Google it. You got a Chromebook? Or Windows all. Troublemaker in chief? Yes, without a doubt. Without a doubt. Yes. Don't really need to ask. I mean, I know you guys pretty well. You just get up and go. I like it.
The 12th, right?
Yes.
Okay.
There's the 12th. There's 2 days for Valentine's Day and I have no plans.
Bowberry biscuits.
That could work. Any homework questions for 3.4 we'd like to go over? That goes for anybody in live stream too. If they have any questions from 3.4 we'd like to talk about or go through, please, by all means, type them up in the chat. We will do them.
We do 25.
25. What other props would we like to look at? 27. I'm willing to venture a guess and say that some people at home might not have started our homework yet, as theirs isn't collected until tomorrow or Monday. No, Tuesday. Any big plans for our extended weekend here, gang?
I have a question about that.
Yeah?
Is it a virtual day on Monday?
Yes, it is.
Okay.
Yes, it is.
I thought you guys-
I'll probably pre-record a video for you guys. Because I won't, well, I'll be here, but I'm not going to teach live to a classroom empty. I might as well just record a video at that point. So, yeah. That's
Wait, why are they out of me?
It's President's Day.
President's Day.
President's Day.
Wednesday next week, I'm going to have your next quiz open up. So that's probably when you should be looking for that. Okay?
It will open on Wednesday.
Yeah. And I think I might give you Wednesday just to work on it. Friday is what I'm thinking right now. Friday is what I'm thinking right now. So yeah. Now we'll probably finish up next unit at the end of next week. So we have 3.6 to talk about, 3.7 and 3.9. Now I'll be honest, I do expect one of those lessons to probably be a 2-day kind of ordeal. If I had to pick one, I would say the lesson that's probably going to have to be is probably optimization, which is calculus and real world setting again, which we didn't do so great with last time around with related rates. So I'm going to venture and say that that's going to be an issue for us as well. Last year, curve sketching 3.6 ended up having to be a 2-day lesson. But I'm hoping that we're going to do better with it this time. Because one, I feel like I've done, despite yesterday and my massive amount of errors yesterday, I feel like I've done a better job explaining what the first derivative test allows us to know, what the second derivative test allows us to know. So I feel like Mr. Kaufman's gotten better as a teacher. So maybe curve sketching will go a little bit quicker and easier. But for us to do curve sketching, it's going to be running our derivative test, finding our critical numbers, and then using that to draw a graph rather than using Desmos or something else. Okay? Nonetheless, let's tackle these two homework questions here, unless anybody else in chat has popped up a homework question. 63, take a look. Okay. Okay, let's start with 27. Find the points of inflection and discuss the concavity of the graph. Okay, so what does this ask us to do? 70 words or less, what's it ask us to do? Second derivative test. Run the second derivative test. That's all it wants. Run the second derivative test. So when I look at 25 and 27, let's go ahead, let's work those out here. 25 has x, and then x minus 4 to the x minus 4 to the third. So there's two ways that we can do this. We can, of course, product and chain rule this, or you could, it is reasonable here to actually put it all into one function as well. You could FOIL all of this out to a cubic and distributed x through. I'm just going to do it as a product and a chain rule though. So here's f and g for us, f and g. Derivative of f, of course, is going to be 1. Derivative of g is actually going to be 3, x minus 4 to the squared. So when I set up my product rule here, let's see here, we got derivative of f times g, so I got x minus 4 to the third, because it's just derivative of f, which is 1. Plus, I'm going to have 3 times x minus 4 quantity squared times x. So this is my first derivative here, third, and 3x, x minus 4 quantity squared. So this is our first derivative right here. Are we all okay with this so far? Okay, we'll run our second derivative test now. For that, we're going to, of course, need the second derivative. So when I start setting up the second derivative here, this one will work real easily, 3x minus 4 quantity squared, plus this is going to have to be another product rule here. Or once again, you could, it is reasonable here, to FOIL this out and distribute. If you'd rather do that here, you can. I'll show it this time just because I did the product rule for the first one, so I'll do the FOIL out this time. X minus 4, x minus 4, this is going to give us 3x, this is going to give us x squared minus 8x plus 16. And you can distribute that through and get 3x to the third minus 24x squared and plus 48x. So when we go to do the second derivative here, as we said, this first one here is going to give us x minus 4 with the 3 out front and 2 there. And this is going to give us 3x cubed, or 3x cubed, this is going to give us 9x squared. This is going to give us minus 48x and plus 48 as we take our second derivative there. Questions here? I do highly recommend that we simplify all this down. So I am going to go ahead and distribute once again. And what I'm going to get here is I'm actually going to get 3x squared minus 24x and plus 48. So I can put all this together with my already existing 9x squared, 48x, and plus 48. Okay? So really the question here is all about, like, can you finally get to the second derivative? Second derivative finally comes out to be, with all of our combined terms here, we got 12x squared. This is going to be 24 and 48. That's going to give us 72x. And 48 and 48 is going to be 96. So this is our second derivative equation. A long way to go to get there, but we finally got there. Questions so far? Really, I think the biggest thing here is, I mean, it's just a lot of algebra. It's just a lot of places where you can make a simple mistake, adding, subtracting, things like that. From here, we're going to set it equal to 0, which means that we're going to try to factor this thing. And luckily, I do see that everything here is divisible by 12, so I'm going to take the 12 out. That's going to give us x squared minus 6x, and that's going to become 8. Which is actually factorable. That's going to become x minus 4 and x minus 2. So it gives us values of x equal 4 and x equal 2. That's what's going to go on my number line, is 2 and 4. So those are my points of inflection. Is that x equal 2, x equal 4? For us to know what they truly are, we need to go back to the very beginning and plug them in. When I plug them in, well, you can find the y values yourself. From here, we're going to actually run the test. We'll actually run the test. So if I put in something less than this, if I put in, let's say, like a 1, what's going to happen? I'll have 1 minus 6, which gives me -5, plus 8 gives me a positive times 12. So I'm looking at plus right there. If I put in something in between, let's say 3, I'm going to get 9 minus 18, which is -9, plus 8, which is still -1. So I get a negative here. Anything on the other side of 4, let's say 5 squared is 25, minus 30 is still, or minus 30 is -5, plus 8 is +3, so we're back to plus. So now we can do our concavity. We have points inflection, so inflect at 2 whatever and 4 whatever, and we are concave up between -infinite to 2 and 4 through infinite, and concave down between 2 and 4. Questions here for number 25. A long way to go to get there, but we got there. Questions? I'm not going to redo the whole thing for 27, okay? But I will get us down to the second derivative. After we get to that point, it should be clear what we're going to do. Questions here about 25. 27, we got x square root x plus 3. So same direction, same plan of attack. So we have our starting function here, f of x square root x plus 3. Of course, we're going to rewrite that as x plus 3 to the 1/2. So first derivative here, it's a product rule, f and g. F derivative, of course, 1. G derivative is going to be 1 over 2 square root x plus 3. So when we set up our product rule here, f derivative times g, well, that's just going to be x plus 3 to the 1/2 plus g derivative f, which is going to be x over 2 square root x plus 3. Questions here? Concerns here? Now, there's two approaches you can take from this standpoint. There's two approaches you can take here. You can do a chain and do a quotient and do them separately. Absolutely can do that. Or you can put them together and make one cohesive fraction and then do a quotient, which is what I'm going to do because I actually think that's easier. Because if I'm going to have to do a quotient rule anyway, I might as well just do one rule and be done. Do my algebra now rather than do my algebra later. So what I can do here is multiply the top and the bottom by the root that I need. So I'm going to rewrite this as square root x plus 3. To make this a common denominator, I'm going to bring in x plus 2 over x plus 3 on the top and bottom. So this gives me 2 x plus 3 which then I can distribute my 2 and combine with my second fraction over here. And this gives me one nice cohesive top of 3x plus 6 all over 2 square root x plus 3. Are we all okay with how I combined my first derivative down? I'd much rather do it now than later, is what I really like to get to. So now when I do my second derivative, it's very clearly a quotient rule. So f's derivative will be 3. G's derivative here is going to be, well, the exact same thing it was earlier. When we take the derivative here of 2 square root x plus 3, we're going to get 2 times 1/2. The only thing there is that 1/2 goes away, and we're really just left with 1 over x plus 3 here as our root. So that's our g derivative. So when we set this up, g times f derivative, f times g derivative all over g squared. What we're looking at here is 2 square root x plus 3 times 3 minus our f, which is 3x plus 6 times our g derivative, which is square root x plus 3, all over 2 square root x plus 3 quantity squared. So now we got some more work to do for sure. We're going to go ahead and put this together here. And I'm also going to start working to combine my numerator into one cohesive fraction. So I'm going to do all that in kind of one step here. This is going to be 3 and x plus 3 all over square root x plus 3 minus 3x plus 6 over square root x plus 3. And simplify my numerator, I'm going to get 4x plus 3. Lots of algebra fun, huh? Lots of algebra fun. Let's distribute our 6 through, and let's go ahead, let's reduce. So this is going to be 6x plus 18 minus 3x minus 6 all over square root x plus 3 all over 4x plus 12. Let's go ahead, let's reduce. We got 3x minus 3x plus 12 all over square root x plus 3, 4x plus 12. And that's what we're looking at there. So we can finally put it all together if we'd like. But honestly, from this point, you should be able to find your zeros. You should be able to find your critical values. We're going to have x equals 0 as a critical value. We're going to have x equal to -3 as a critical value. And that should line up pretty decently for us. Those should be our two that we're looking at here, because -3 is the same value for here. But that one goes to 0 just as much as it is for the root that goes to 0. So it actually works on both one there. Questions? Okay. 27. Yeah, I think you can see when I said at the beginning of the year that I can fill this board with a first derivative test or a second derivative test. I think you see where that really comes in. It's not really so much on the actual calculus end of it. It's really just on the combining and working your algebra down. It's really working just the basics of let's put these together, let's simplify this, let's simplify that. That's really where a majority of your work takes place in calculus. The calculus part is the derivative. That's done. It's simplifying that out where you go back to what you did in Math 2 and in Math 3 where it gets challenging. Let's take a look at 63 so we can be done with homework problems. What we have here is the graph of f is shown. We want to graph f's derivative and f's second derivative on the same coordinate axis. So we're looking at 63. So 63 is a standard cubic function, or relatively standard cubic function like this. So this is, of course, f. So our second derivative, or our first derivative, would be a quadratic function, so a parabola. And then our second derivative would be one less from the parabola, which would be a line. That's what I'm looking for. That's what I'm looking for. Questions? Okay. Whew. Got me doing a whole bunch of stuff today. Ladies. Our gentlemen aren't here, so ladies. Okay. How we doing with our warm-up problems? How we doing with our warm-up problems? Do you remember how to do synthetic division?
Nope. I watched the video.
No, but you watched the video, looked at a
Now we know
picture.
how.
Okay, let's rewind the clock back to Math 3 honors. We need a box number. What's the box number here? 3. We take this group, the divider group, set it equal to 0, solve it down. 3. Okay, I'm going to list out the coefficients. We're going to go from highest to lowest. If for some reason I don't have one, I'll skip it and put a 0 in its place. So I start with my x to the 4th power term. If for some reason I didn't have a cubic function, I would put 0. But I do. I have 9. I got negative 12. And I've got negative 79. And I've got 60. Okay? First number always comes down. Don't do anything to it. So 2 comes down. Now what are we going to do with 2? Multiply by 3, it gives me 6, right? What are we doing here? Add or subtracting? What do you think? Okay, so Bianca says Adam, Fatima says subtracting. Alex says Adam. Okay, so here's why I'm making you do this. My last problem has synthetic division. We are going to add them up. We are going to combine them as they are. We are going to add them. So when I add them, what do I get? 15 times 3 again gives me 45. We combine them. What are we going to get? Multiply again. What are we going to get? 99. Combine them again. We're going to get. And combine them again, and we get 0. Okay, why is that important that the last one is 0? What does that mean? Well, it means we have no remainder. Guess what we will have? We will have remainders. Now, what this means, of course, is now I can just move all of my powers down. When this was x to the 4th, so now this is x cubed plus x squared plus x and plus my number, right? Okay. Do you think that this one's going to work out so nicely? Probably not. Especially because Mr. Kaufman deliberately made up the first one. I just picked random numbers for the second one. Okay, so our box number here will be -1. We got 6, 9, negative 12, and negative 45. 19, not 9. Okay, bring the first one down. 6 times -1 is -6. That makes 13. -1 times 13 is -13. That gives us -25. And -1 times 25 is +25, which gives us -20. We do have a remainder, as intended. So we have 6. This was x cubed. Now it's x squared. This was x squared. Now it's x. And this is just our number. What do I do with this? I put it over the divider still. Over x plus 1. It's a fraction. Leave it as 1. Questions? Issues? Concerns? I'm so excited. And I just can't hide it. Okay, my easy one. My easy one. What can I do here?
Rationalize.
Nope. It's an easier way. Yes, you can do it that way. Absolutely. It would work. There's an easier way. How?
Yeah.
Yeah, there's a property of roots that I can, since they're both square roots, I can just merge that in to 1, right? Which gives me, right? Now, if you rationalized it, you still should have gotten the right answer. You would have ended up with you probably ended up with 9 root 2 over, or something like that, or 18 over 2, right?
I just got square root 324 over 2, which is just 18 over 2.
So, today, we are shifting gears a little bit. We are going to go away from our first derivative and second derivative test for today. We will be back with them on Monday, I assure you, when we talk about curve sketching. But today, we are going to talk about infinity again, specifically limits, and limits dealing with infinity. The reason why we're going to do this is because this is going to help us sketch curves at the end of the day, because it's going to tell us where everything is going. Where everything is going. Whether we're going upwards for forever, downwards forever, how much are we increasing and decreasing by? So this will be vital for us when we do read curve sketching on Monday. Now, most of that information we're going to gain from the first and second derivative test, albeit that is true. However, this stuff that we're going to talk about today is important in A, helping us with the other facets of it, and B, it's also going to be important when we come back around to doing integrals later on. Those of you looking at me sideways, Callie, integrals are the opposites of derivatives. So we spent all this time working on calculus version of adding. Eventually, we will have to get to calculus' version of subtracting. So let's move on here. Let's start with slide 2. Slide 2. So let's look at a nice standard rational graph of 2x plus 6 over x plus 5. So there is what type of asymptote here? We have a vertical asymptote. We have a vertical asymptote. There is a horizontal one as well. But I want to look at the vertical asymptote at x equals 5, right? Now, if I asked you to do the one-sided limits here, what would you tell me? What would you tell me the one-sided limit is coming in from the right side? What is that going to be? From the right, it is not positive. At the right, it's coming at negative infinite. Okay, coming in from the left side, it will be positive infinite. So we call these, of course, infinite limits, because one-sided, they do come into infinity. And we did talk briefly about how we can claim a limit goes to infinity so long as the limits agree that they're going to the same infinite here, right? So we did talk about that way back in Unit 1 when we talked about limits. However, that's not the situation here because these two don't agree. They're not both going towards positive. They're not both going towards negative. So we can't kind of fudge the numbers and say the limit at 5 would be infinite. The limit at 5 is actually no limit at all, but it continues to go on and up forever, right? However, using these one-sided limits, you could still sketch a pretty good picture here of what's happening. You know at 5, that is not going to be existed, right? You know the limit at 5 doesn't exist, but if I gave you the other two, if I gave you all three, if I wrote out limit of 5 does not exist, limit as it goes to negative 5 is negative infinite, limit as it goes negative 5 from the other side is positive infinite, you would be able to tell me, well, Mr. Coppin, that's got to be an asymptote. And on this side, we're curving down. On that side, we're curving up, right? So you can see already, like I was saying, first derivative test would tell me increasing and decreasing here. We would be increasing along the left side and along the right side. This graph is consistently always increasing. It's always going up. Second derivative test will tell me that that one's concave up and the other one's concave down. And using these limits also allows me to tell you where the asymptote is. So these three ideas combine to help me have a very good picture of a graph, especially ones that Desmos isn't going to want to graph for us because they're going to be too complicated and they're going to have holes in them and breaks in them, and Desmos doesn't like that. So let's look at this one. Let's continue with this function, okay? So what would you say, and this is something that we did also in Unit 1 where I said x is going to go towards infinite, right? So as x goes forward, as x goes to the right forever and ever and ever, where is the y value going towards? And this goes back to what Callie said a minute ago. We talked about the vertical asymptote, so now I'm asking you about the horizontal asymptote. What is the horizontal asymptote here? Looks like it's about 2, right? So this is where we can talk about end behavior. If you remember talking about that back in Math 3, you talked about end behavior. What happens as we go outwards, left and right, forever and ever and ever? Well, right here, we're going to talk about them as limits at infinity, going towards the limit at x equal infinite or x equal negative infinite. And this gives us our horizontal asymptote. This is where these are going to come back to play. Questions here? Issues here? So let's make this clear. If these two agree, if the limit as x goes to infinite and x goes to negative infinite, if these two, as we shoot off towards the right forever and left forever, if they spit out the same value, then that value is the horizontal asymptote. So it's a little bit different than the other one. So as I go to a specific value, if I shoot off towards infinite and negative infinite, we have a vertical asymptote. And as x goes outwards forever, we talk about horizontal. So this is very detail-oriented right here. -5. X going to a specific number. And that gave us limits at infinity. This gave us limits of infinity, or infinite limits, right? Now on slide 3, we are talking about as x doesn't go towards a number, x going on forever and ever and ever to the right, or x going forever and ever to the left. What does the graph go towards? So the first one is talking about x at a specific point being a vertical asymptote. On slide 3, we're talking about not x at a specific point, but as we go forever, where is the horizontal asymptote? Does that make sense? You have to read your limit very carefully here, is what I'm trying to stress to you all. Let's go on to slide 4, if we're ready. So, can you determine these limits for us quickly? Can you determine these limits for us quickly? You can think about it logically. You can think about it with a graph if you want. You could do a couple of evaluations. What are we going to have here? We are overthinking this question. We are overthinking this question. Let's start with the first one. As my numbers get bigger on the bottom, what's going to happen to the fraction overall? I'm going to start with 1 over 1, right? It's just 1. Next one's going to be 1 over 2. Then 1 over 3, 1 over 4, 1 over 5, 1 over 6. Where are we going? To 0. Are we ever going to dip down into the negatives? Could we ever actually reach 0? No, but that's where we're going, right? Okay, what about the next one? Is that any different? No, it just takes a little bit longer to get there. What about the third one? 1 to the 5th power is 5. 2 to the 5th power. Do you know what 2 to the 5th power is? 128. No, it's not. 2 to the 4th power is 16. 2 to the 5th power is 32. Okay, but 3 to the 3rd power, 3 to the 5th power is a very large number. It is a very large number. I don't know. You have to type it in. So it gets there increasingly fast. So what I want to do today, the goal for a bit of today, is to give you guys a couple of tools, a couple of tips to reading these limits, reading these functions, and being able to know what does it look like, where are the limits going to take me, where is the derivative going to take me. Okay? So this is my first little tip here. If we have a positive rational number, positive rational expression. So if I have a number on top and on x is my bottom, if x has a positive exponent, meaning that x will stay in the denominator, then I'm going to go to 0. I'm going to go to 0. If I have just a number on the top, and I have some power of x on the bottom, so long as it stays on the bottom, which it should, it doesn't matter if I go to the right forever or the left forever, we're going to go to 0. Questions here? Concerns here? Okay, let's go ahead. Let's move on to my next slide. I tried to include a lot of my work in my slides today to kind of help with some of the issues we had yesterday, and also for anybody at home, should the live stream die again because of Mr. Coffin's fat fingers hitting the wrong buttons, they can still keep up on their own. So let's move on here. Let's move on to slide, what is that, slide 5 now, right? Okay, so let's talk about these two. Let's talk about these two problems. Let's start with the first one. Let's start with the limit of 5 minus 2 over x squared. Now let's do this analytically here, but let's do it with a little bit of play. So I have the limit as x goes towards infinite of 5 minus 2 over x squared. So let's go ahead, let's separate these two limits and do each one individually. The limit as x goes to infinite of 5. The limit of a constant number is that number, yes? So this first term breaks up as 5. Okay, the second one here, the limit as x goes to infinite, 2 over x squared. We just talked about this. This is going to be what? 0. So minus 0. So the limit overall is 5. Questions here? So we call this method direct substitution. Direct substitution. So in other words, if I swap this out for infinite, what happens here? This goes to 0, right? This is our method of direct substitution. So, what do you think we're going to do on the next one? What did I have you do at the very beginning of class today? I reminded you, I should say, how to do division. So, when I look at this next problem, when I look at example 2 here, I'm going to divide. Now, you can either do long division or you can do synthetic. I did synthetic earlier, but I'll show this one with long division. So if I want to take my example 2 here, 2x minus 1 would go in, not my root, this is just standard division, Mr. Kaufman. Standard division. Let's try that all over again because it looks terrible. Standard division, not a root, Mr. Kaufman, come on. I'm so used to drawing roots that it's hard not to. 2x minus 1 being divided by x plus 1. Do you remember how to do it this way? What number do I need to multiply this by to make the x's match up? 2. We're going to multiply by negative 2. So that way, or not negative, positive 2. So I got 2x plus 2. We will subtract these. So the x's cancel. 1 minus 2 is negative 3. So this would be my remainder. So what I have here, what I've been able to show is that x plus 1 over 2x 2x minus 1 over x plus 1 is going to be equal to 2 with a remainder of 3 over x plus 1. And now I can do it just like I did the last problem. This is still the limit as x goes to infinite. So I can separate x goes to infinite of 2 minus the limit as x goes to infinite of 3 over x plus 1. This one is going to be 2. This one, when I direct substitute in, gives me 3 over infinite, which is going to be 2 minus 0, which is still 2. Questions here? Now, how much fun was that? Wouldn't it be great if Mr. Kaufman gave us some rules to use so we never had to do it again? That's what I intend on doing today. So that way you don't have to divide these like this every time. Because the only rule you have right now is when there's a singular number on the top. That's why we couldn't do it from the very beginning, because it's not a single number. There is x on the top, so the only rule you know right now has to have numbers on the top. No x's up there, so we had to get that x out. That's why we did this division step right here. Okay? So, if direct substitution gives you something where we would have infinite over infinite, like in the second one, we have to get rid of the x's on the top, so we will divide each term. I recommend dividing by the highest power of x that is available to you in that denominator. If I have my choice of x's, I'm going with the highest power of x, because that has the biggest opportunity to get rid of all of the x's in the numerator. Questions here? Now, I won't stress too much about this. We're only going to use this typically when we have higher powers. Like when I have something like 2x cubed plus 7 divided by 2x to the 4th plus 8. When we have high powers, that's when we'll go ahead and divide. That's when we're actually going to have to go back and either use synthetic division or use long division to help us. Okay? Ideally, if the powers, if the degrees match, we can do a few other tricks. So for something like example 2, where the degrees match, we do have a few other options available to us. Okay? So let's get into some of the specifics. When are we going to have to do this division? When can we use some other tricks? Okay? So this strategy works really well for evaluating limits. When the degree of the numerator is less than the degree of the denominator. When I have more x's on the bottom than I do on the top, inevitably what is going to happen is we are going to go to 0. Okay? When I look at this function right here, for my next slide, on slide 7 now, 6, slide 6. If the degree of the numerator is less than the degree of the denominator, then inevitably we are going to go to 0. What I'm telling you here is that x squared outpaces the singular x. They're both going towards infinite, but one's going so much faster, so much stronger, that it is outracing the other. So while technically they're both infinite, they're both individually going up for forever. The numerator is going up forever, bottom's going up forever. There's such a disparity between the two at what rate they're going,
which would be a derivative question, that the bottom significantly outpaces and we still end up at 0. Let's show a little work to back this up here. Let's show a little work here to back this up. So if I go with that same idea, I'm going to use my division to prove this to you all. Because I'm not just going to show you my tricks today, I'm going to back them up with reason. So I'm going to take my function, my 2x plus 5, over my 3x squared plus 1. What I'm going to do is I'm going to divide every term by the highest power of x I see. The highest power of x we see, of course, is x squared, right? So what I'm going to do is I'm going to go to every single term, and I'm going to divide them all by an x squared. So that's the step that you see there in blue first. That's the very first step I took in blue. So that gives me this looking monstrosity. 2 over x squared plus 5 over x squared, 3 over x squared, and plus 1 over x squared. This is what we got. Yes? Okay. So take a moment and reduce what you can reduce. I can take away these x squareds. I can take away one of the x's up here, right? Take a moment and reduce what you can reduce. The next step is to do each limit individually. So now we'll do the limit of 2 over x as x goes to infinite, plus the limit of 5 over x squared as x goes to infinite, over limit of 3 as x goes to infinite, plus limit of x goes to infinite, 1 over x squared. And what does each of these give us? Well, this is a number over x, so that's 0. This is a number over some x's, that's also 0. This is a number over x, so that's 0. And this is just a straight out number, so it's just 3. This is where I get the 0 plus 0 and 3 plus 0 for the next step in blue. Questions here? What does all this simplify out to be? 0 over 3, which is, of course, still 0, right? So this is how I have derived. This is how we derive this shortcut. Ultimately, what you need to know is what's up there, the first sentence. If the degree of the numerator is less than the degree of the denominator, then the limit as we go towards infinite are at 0. You don't necessarily have to have the proof below for this. The critical information is that sentence. Okay? If you want, you could even like circle this problem that I have, this example 3, and say proof of that. Okay? Questions here? Okay? Let's roll with, we talked about if the numerator is less, let's talk about when they're equal. Okay, so if the degree, going on to our next slide, going on to our slide 7, if the degree of the numerator is equal to the degree of the denominator, then the limit has a little bit of a different twist. It is going to be a ratio of the leading coefficients. It's going to be a ratio of the coefficients. So when I look at this problem right here, when I look at this one, my limit for 2x squared plus 5 over 3x squared plus 1 is inevitably going to be 2/3. It is going to be the ratio of the leading coefficients. Make no mistake, your leading coefficients is your higher power. If for some reason these aren't in standard form, that's the first thing you should do is put them from highest degree, lowest degree. So if there's like an x to the fourth back here, that would be my new leading coefficient. Are you ready for me to prove this one? I'm going to prove it using the same attack method. I'm just going to go to everything. I'm going to divide by the highest power of x, which is x squared. Just like I did last time, I'm going to go to 2x squared divided by x squared. I'm going to go 5 over x squared, 3 over x squared, 1 over x squared. Then I'm going to reduce. That cancels these x's and cancels these x's. So what do we have when I look at the individual limits? I have limit of 2 as x goes to infinite, plus limit of 5 over x squared, limit of 3 as x goes to infinite, plus limit of 1 over x squared. And what did these spit out? This spits out 2 plus 0, 3 plus 0, which is 2/3. I did this work in blue to try to match that work in blue because I just now remembered that I did all of it in blue every time I did it. I'm trying to color code now. So you see that those are the steps that I took there and here to back up that it has to be 2/3. Questions? Issues? So we talked about where the numerator is less than the denominator. We talked about when they are equal. Let's talk about the last option where the numerator is bigger than the denominator. What will happen? What do you think is going to happen? What do you think will happen? If I have more x's on top than I do on the bottom, where do you think we're going to end up as x grows and grows and grows and grows? Bianca says it's going to go towards infinity. Can you explain your logic to us?
It's like the opposite of what happened with whenever it was greater on the bottom, because your numerator is going to be getting bigger at a faster rate than your denominator.
Okay, so we'll reiterate for anybody that didn't hear. It's the opposite situation of what we described at first. So since there's more x's on top than there will be on the bottom, while they're both going towards infinite, the one on top will significantly outpace the one on the bottom, meaning that it will be able to grow faster and inevitably go towards infinite itself. Albeit maybe a little slower because it's got the bottom dragging it down. It's got the denominator slowing it down. And as we move on to, what is this, slide 9 now? Slide 8, I don't know why I can't get my slide numbers right. Slide 8. That is exactly what we see here. If the numerator is greater than the denominator for degree, if I have more x's up there, we are going to go towards infinite. Now, it is important to note here that you have to know which infinite you are going towards, whether you're going towards positive or negative infinite. And that requires a little bit more thought than perhaps standard. You have to pay attention to what exponents you have and what signs you're going to get out. So for one like this here, where I have 2x cubed, my leading term, my term on top, is an odd power, right? Odd powers can spit out negative and positive answers. So I have to be aware of which way I'm going. If I'm going towards negative infinite, I will go towards negative infinite here. If I'm going towards positive infinite, we're going to get positive infinite. Now, if I have an even powers only spit out positive numbers, right? X to the 4th, x to the 6th is only going to spit out positive numbers. So you do need to pay attention to what's going to happen. Okay? You do got to pay attention to your signs here a little bit. So this one requires just a little bit more of a deeper dive when we talk about it. So I'm going to go ahead, I'll prove it the same way. And I think this is the way that you ultimately should try to figure out which way you're going to go. As you've seen, this isn't really that difficult. It looked weird the first time I did it, I'm sure, but I think maybe now you guys got it. Okay, so let's go ahead, let's repeat the process here again for this problem to back up which way we're going. So 2x to the third plus 5 over 3x squared plus 1. So I'm going to go and I'm going to divide everything by the highest power of x, which in this case is x to the third. So 2x to the third over x to the third, 5x to the third, 3x squared over x to the third, and 1 over x to the third. We'll go ahead and we'll simplify. And when we simplify, these x's go away, and so do these ones. So what am I left with here? I'm left with 2 plus 5 over x to the third, 3 over x, and 1 over x cubed. Right? And as I start doing each limit individually, I'm not going to write them every time because I'm getting tired of writing it. We're going to get 2, 0, 0, 0. Which would be technically undefined, wouldn't it? And that's how we key in, that's where I'm going. That's where I'm going. Questions? Issues?
What would it look like if it was going towards negative?
This is just to cue us in that it's going towards a infinite.
Oh, okay.
If we want to know which one specifically, I recommend doing a little tree, little guess and test method. I think that works really well.
So when it's undefined, that's when you know it's infinite.
Yes, when this spits out an undefined, we know that we're going to go towards an infinite. Because what we're legitimately saying here is that the horizontal asymptote is not defined. There is not a specific horizontal asymptote. Therefore, there isn't one. So there's no limitation, so go. Go red. So let's move on to the next slide, what is now officially slide 9. I got 3 problems. I would really like for you guys to work these 3 problems because I am very tired of talking. Very tired of talking. If anybody in our live stream has questions, they can go ahead and ask them. When we're working slide 9, I'd like you to work out these 3 problems, please. Tell me what these limits are.
Just the answer will do, to be honest. I'll work them out.
If anybody needs me to work them out, that's what I'll do. Okay. Pretty much ready to go here. We're pretty much ready to go here. Let's start with example number 6. go with example 6. What's our limit here? 0. Why? The degree of the denominator is bigger than the degree of the numerator. So we're going to 0. Very good. Next one. Degree of the denominator is bigger than the degree of the numerator. So the very first one, we're going to 0.
Oh, I thought you were going to say.
Oh, no. Now we're doing the second one. Where are we going for the second one, man? Where are we going?
One?
We're not going to 1 for the second one. That's not the leading coefficients. What's the ratio of the leading coefficients here? -2 over 3. Yeah, -2 over 3 for example 7. Yeah, that's one of those ones that I said earlier. Make sure that if it's not in standard form, you take a second to rewrite it. That -2x should go in front, and technically that +3 should go on the back of that numerator. What about our last one? Where are we going here?
I got you. 0.
Nope.
Why is it not 0?
I'm glad you asked. So, when your limit involves a square root, things get a little bit more sticky. So, to answer Callie's question, that was totally planned for a setup to segue into the next slide, for slide 10. Let's talk about what we will do when we have to involve roots. And you will see why it doesn't work, or I can loop back to why it won't work, okay? So, let's take this one here. What we're going to do is we're going to do a little sneaky substitution here. Little sneakiness, okay? We are going to divide everything by, my motion doesn't want to go here. Hold on. Here we go. Okay, so we're going to still divide, but we're going to divide by x. When we divide by x, we're going to do that for the numerator, but for the denominator, we're going to do something a little different. The denominator, we're going to divide by the square root of x squared. That way, my third warm-up problem can come back into play, and I can combine roots a little bit and bring the x in to the root. Does that make sense? Square root of x squared is still x, right? So instead of just dividing by a normal x, I want to divide by a setting that I can actually bring into the square root on the bottom. So when I look at this one here, the limit of 3x minus 2 over the square root of 2x squared plus 1, I'm going to divide the top by x. I'm going to divide the bottom by square root x squared. So what ends up happening here is my top is going to reduce down to be 3 minus 2x, just like it did on the past couple of times where I had approved. However, the bottom allows me to bring that x squared in because it's already a root. So now I have 2x squared over x squared plus 1 over x squared. Are we all okay with what I have done? Yes? No? Okay. Simplify what we can. Get rid of these x squareds. So, that is the first 2 steps I've taken, first 3 steps I've taken in blue. From here, we are going to go ahead and do the limit. Now, when we do this limit, we're going to do these 2. We're going to do the limit inside this root. Inside of this root. So what ends up happening here? What ends up happening here? So what's going to happen here when I do the limit for this one here? So let's do limit, 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 limit. It's going on, taking place inside this square root. Okay, that's what I want you to make sure you're aware of. So I'm going to be left with 3 minus 0, correct, on the top. Underneath, inside my root, I'm going to have 2 plus 0. This reduces down to be 3 over square root 2. 3 over square root 2. Questions here. Concerns here. Now, this is for, say it one more time, this is only for x going towards positive infinite. When we go towards negative infinite, we have to do something a little bit differently. It's almost the same, but because it's not positive infinite anymore and we're dealing with roots, and positives and negatives have some weird things with roots where we sometimes get an imaginary complex, which we're trying to avoid. We have to do a little bit different plan for when we go to negative infinite. Before I move on, are we all set? There is no quick, easy way to do this one. There is no quick, easy rule, I think, for this one. I think for this one right here, for roots, it is best to just do it yourself. Because it's difficult to see what the coefficients are going to necessarily be, because sometimes things alter and change. So it's not as easy as saying, well, it's going to still be 3 and root 2, because you don't know necessarily how that square root's going to play out sometimes.
Could you look at example 8 for the last slide?
Pardon?
If it's it.
I'll loop back to it, remind me, okay? I'll loop back to it. So, let's talk about going towards negative infinite. So like I said, on our next slide here, this is slide 10, if I'm keeping pace correctly. No, I'm not, slide 11. Slide 11. So when we go towards negative infinite, we are going to have a different situation. We're still going to divide, but instead this time, we're going to divide the root, we're going to divide it as a negative root x squared. We're going to divide it by a negative root x squared. Everything else is going to stay the same. So let me go ahead, let me put this problem up, which is actually the same question, it's just going the opposite way out. So let's get back to where we started. So this time, I'm going to divide the bottom here by negative, because it is plus and minus when it comes out of the root, right? So if I'm going towards positive, I'm going to use the positive version of root x squared. If I'm going towards a negative infinite, I'm going to use the negative version of the root. Okay? And that's really what we're doing here. Now, everything else is going to take place the exact same way. 3 over x minus 2 over x square root involved here, and I'm going to get negative. And I'm going to have my 2x squared over x squared plus 1 over x squared. Where's my keyboard? So that's the work that you're going to see here, and of course, red. We go ahead and reduce. Okay, so I'm going to get these x squareds. I'm going to get these x's. We'll do each limit. Once again, this is going to take place inside this root. And what do I have left? I have 3 minus 0 over negative root 2. So 3 negative 3 over root 2. Questions here about this one? So you do have to be cautious of which way you're going when roots are involved. Questions here, concerns here. I don't know if anybody on our live stream is even still watching, because I typed a question up there and nobody answered. Maybe they all just fell back asleep. I don't know. I know yesterday it didn't work well, but I really do think that the live streaming is better than pre-recorded videos. Are we ready to move on?
Okay. So, let's talk about another situation, which is why I said I don't want to do that, glued back to that one quite yet, because we're not quite finished. So, why did I make you guys do synthetic division today? For these problems coming up. So, moving on to our next slide. Slide number 12. Oh wait, some people responded. Allie and Michaela responded. Well, at least I know those two are here. So, when your limit at infinity does not exist, or when we would otherwise approach infinity, right? That's what we talked about earlier, right? We did that earlier with 2 plus 0 over 0 plus 0, right? It's okay, it's going towards infinite, right? So what ends up happening, what's actually happening on your graph is you don't have a horizontal asymptote anymore, you have a slanted asymptote. Your asymptote is not a single number, it's actually another line. It's actually a derivative of something. So, yeah. Weird, I know, right? Like, technically speaking, there's always a horizontal asymptote. It's just that it's not at a specific number anymore. So if we're going upwards forever, we're actually approaching something. There is a line, it's just a function. So like something like this here, let me put an example up here. So if we look at like the function like limit of, let's say, 3x squared plus 1 over x minus 1, right? So you would tell me that this is going towards infinite, right? As x goes towards infinite, right? Okay, so technically, yes, this is true. The y values are going on and on and on forever, okay? But what's actually happening is as you look at your graph here, so somewhere out here, we have our vertical asymptote here at 1, right? And as we continue upwards, okay, what's going to end up happening is it's going to go off like this, right? So there's actually a line, some line or some function that it's trying to match. Some y equal mx plus b. Or maybe it's some y equal ax squared. Maybe it's a parabola that it's trying to match. There is something that it's being gravitated towards. It's just not a specific number anymore. It's slowly and surely becoming a different function. So as we get way out there, the two actually become almost identical. You've seen this a couple of times, and we've played it off as something else. Make no mistake, you've seen this. You absolutely have. You did it in Math 2, and you saw it in Math 3, and you even saw it sometimes in pre-calc. Whereas as this goes on, it continues to do this, but it never actually stops going up. It just continues to get slower, right? It's flattening out. It's approaching a line. It's hard to explain that to somebody in Math 2, that this function, that once it gets past a certain point, it basically is a line. Even though it wasn't to start with, at this point, from this point forward, it might as well be a line. Or this function didn't start out as a parabola, but as it's going on and on and on, it might as well have been a parabola, right? So that's what this is saying. So the question is how do I find that thing? How do I find what is it trying to mimic? What is it trying to become? What does it look like when it finally gets out there? And that's where this comes in. When we go towards infinite, when the limit is infinite, we should be able to figure out what function we are eventually going to end up mimicking, looking like, approaching. So, to determine this, as we go towards positive or negative infinite, we can find this particular equation, which is where this is going to come back. So, what you need to do, what that function is the actual divided out function.
is the actual divided out function. So even though it's going on and on and on forever, it's what would this actually be if we simplify it? So when I take this one here, and I take 2x squared minus 4x, and I divide it by x plus 1, it gives me a box number -1, 2, -4, and 0, because I have no constant term, so the 0 there is important. Bring down the first number, 2 times -1, -2. -6 times 1 is +6. So the function that we are approaching, this limit as it goes towards infinite, our asymptote, our slanted asymptote, would be at this function. So our asymptote would be at the function y equal to 2x minus 6 plus 6 over x plus 1, because we have a remainder here. That is the line that my asymptote is actually going towards. Now, if we run the limit of this, it's going to say infinite still. This is where my asymptote is. So if I want to do the limit, this would be infinite minus 6 plus 0, which is still infinite, right? But this is where this is what function it's mimicking. This is what function it's heading towards. Questions here? So the answer is still the same. The limit is still going towards infinite. But this is where that slanted asymptote is. This is a line. And this is where the asymptote would be. You're just so used to the asymptotes being hard numbers. X equal this, y equal that. That the idea that it could be a regular equation feels foreign to you now. Right? But x equal a number is still an equation. It's still a line. Y equal a number is still an equation. It's a line. It's just a horizontal or vertical one. So what if it's not horizontal or vertical? This is what we're looking at now. That's where I got this from. Okay? And what's more is you can still run the limit off of this asymptote. This asymptote will still tell you whether we're going towards positive or negative infinite. So that moves back to our question earlier. How would I know which one is it? Do it. Do the synthetic division to find out which one we're going towards. That's my advice to you. Synthetic division is easy, really easy. Do it, slam it in, back into the limit, and grind it up. That's how I know whether I'm going towards positive or negative. I don't worry about whether, is this going to be cubic? Is that going to be? No, I don't worry about all that crap. I do the division and then I move on. Questions? Okay, that's it for today. That's it for my live stream for today, at least. So, those who are at home, you guys can go ahead and peace out.
Are you gonna go back to example 8?
I will for you guys here. Okay, but I'm going to go ahead and let the live stream peace out. We're going to get started with our homework here, and we'll move on. Okay, so those of you guys on the live stream, unless you have questions, I will see you all next time. Have your homework ready on Monday. Or Tuesday, sorry, Tuesday. If the rest of you guys want to start your homework, that's fine. I will loop back to that question. Did I go past it?
Yeah, you're back to example 2. It's number 8. Yeah.
Okay. Nope, there's no plus. Just 5 over. Okay. You guys are right, and I am wrong. And now see what I did. I had a dyslexic moment. It's not supposed to be 3/2, it's supposed to be 2/3. Or no, sorry. I have it wrong. You guys had it right. You guys had it right. Bottom
So it's
is,
supposed to be 0.
it should be 0. So that's my bad. Had a moment there. Got things backwards. Yeah. I had a dyslexia moment and put the numerator on. I have my fraction upside down. I meant for the bottom to be on top and the top to be on bottom. You guys need the homework back up there? I'll put it back up for you. I have fixed that on the slides now. Ladies, it is about that time to start packing up. I might do something different for Monday as well and save our lesson for Tuesday. So just pay attention to whatever I put up on campus, okay? Make sure that you're ready and raring to go, because I might just decide that, well, maybe some practice with first derivative, second derivative test and stuff like that might be better used for Monday on the day that you're at home, rather than trying to do new lessons. So I might just let you guys do some IXL work or something like that.